Good afternoon. Today we will look at processes, but from the more abstract view. We saw the processes on the kernel view as data structure and the top of the stack, and the kernel switches between the stacks of individual processes. Now we will look at top level of processes seen from the perspective of user program. A process has two meanings. First is dynamic sequence of operations performed under control of operating system, just the sequence of processor instructions. Static aspect is set of resources collected to let the process run. So minimum set of resources is a processor and memory, some part of memory allocated to the process. But many times we have some devices, real or virtual, some procedures allocated by operating system, library procedure to let the program run, some system variables, and so on. The basic is to let the processes run in parallel without spending too much time for operating system own activities. So acceptably short response time. Allocating the resources and deallocating the resources from processes, providing mechanisms for inter-process communication and synchronization, and providing mechanisms for creating and finishing of processes. We talked about creating processes last week. This is the picture that we know already, how the process switch is performed, so we can skip it. Here, there are example situations in which a process can be created. For example, when the system starts, some processes are automatically created. Minimum is one process. For example, in Linux, we have one process called init that is the ancestor of all other processes. On user order, when we, for example, type the name of the file and press enter, operating system loads a program from this file and starts a process to execute this program. Call from the application, a program can run another program. For example, in Linux, we have shell, which is a program, because in Linux, we don't have any built-in command interpreter. And each program runs other programs. Run a batch job. It creates set of processes that take every job in the batch and create a process to run this program. On acceptance of interrupt in real-time system, it can start a process to serve the device that sent the interrupt, and so on. In fact, all those operations are finally executed as some interrupt. When we type name of the file containing a process, we enter the last key pressed is enter, and the reaction of system to this interrupt is run in a program. And other situations are in fact interrupts as well. Termination of a process, it can result from the willing of the program. It can be executed as the order of the parent of the program. It can be illegal instruction or division by zero, an error. The compiler can build in the program some control operations. For example, checking every pointer before use if it's not a null pointer. If it's null pointer, extra code finishing the process can be called. The order from other process, for example, kill signal from the parent. And again, all above are in fact various kinds of interrupts. Let's look at the states of a process. First, we have a state running. It has various names in operating system: active, running, current. It is the program or process that has allocated the processor, so it runs. The instructions executed by the processor are instructions of the program. When there are not enough processors to run all the processes, there are ready processes that are waiting for processor. Typically, we have more processes than processors, so they wait in ready state. Blocked state, and the name of this state is always ready. No other names are used. The blocked process, here we have various names like suspended, deferred, delayed, non-active. That's all for now. It means that the process waits for some event other than processor allocation. For example, it waits for a device which is occupied by other process. It waits for enlarging of address space of the process because the space that it has is not enough. Waiting for data from another process. Waiting for given time on the clock. All those conditions or events change the blocked state to ready. They never change to running. Why? Because these decisions, 2 and 3, are made by the system scheduler. that allocates processors to processes. This decision to unblock the process is made on higher levels of abstraction. Different levels of operating system are responsible for unblocking. For example, if we wait for opening a file, it is responsibility of file system level. If we wait for enlarging memory, it is memory allocation level, and so on. So a running process decides that it wants to wait for something. We change its state to blocked, and when the event occurs, the process state is changed to ready and can be taken into account by the scheduler. These are examples of states of processes in Unix. The graph of states is very complicated, not necessarily, because, but you know that Unix was made by non-specialists in computer engineering. In fact, we have running, we know this state, divided into two states, kernel running or user running. It just distinguishes if the process is inside the operating system or in user state. It's okay. Ready in memory corresponds to ready, simply. All other states, except zombie, are blocked. Blocked with waiting on some event. For example, swapped waits for allocation of memory to the process. No, it should be swept. In the literature for this state, we use sweeping, not swapping. But again, it was created by non-specialists. Zombie is a special state. Zombie, generally, processes in Unix-like systems are asynchronous. We can ask for a state for a given process, but we never know if the process exists. So our call could be dummy. And it is typical behavior of a process. Then a process creates a child and delegates some activity to the child, then waits until the child has finished. For example, fast sorting. A process takes a file, cuts the file into pieces, and creates a child to sort every piece. Then it merges sorted pieces of the file. So the parent process should know when the child process is finished sorting the parts of the file. But it can happen that a process creates a child and the child finishes immediately for some reason. And when the parent asks for a child if it's alive, now this process disappeared. There is no process of such ID in the system. Because processes are asynchronous to each other. This is synchronizing those processes. A child, when finishes, changes to state zombie. Zombie is a state in which a child waits for the parent to ask for a state of the child. Now, the parent can ask after a second, minute, or hour if the child still is alive, because it waits in some special state. Of course, it need not have any code or data. It is just the descriptor and state, nothing more. And the zombie state is created to non-existent, we can say, when the parent asks for the state of the child, or the parent finishes. When the parent finished, it will not ask for anything. So it's a special property of Unix-like systems, the zombie state. This is the graph of states. Please do not look at this graph. It's overcomplicated. It's constructed non-professionally, I can say. So let us skip it. Typically, when a process executes and wants some service to be performed by operating system, it calls some layers of operating system, but typical situation is with the exception of synchronization primitives that directly refer to microkernel. User program call comes through the layers of operating system. It comes through file system. File system is lower. Here is the program supervisor, we can say, file system and device drivers, for example. And a process migrates through those layers. And when the process acts here, it is a user process. When it crosses the barrier between user programs and operating system, it becomes system process and has a process descriptor in the system. When it comes to microkernel, it is not a process anymore, because in processes, in the kernel, the processes are data structure, process descriptors. Just kernel incarnates to one process or another. And the process that runs on a processor is only one process, in fact. And part of kernel that deals with states of processes and chooses a process to run is scheduler. It operates on process array, which need not be array. In Phoenix, for example, it is the tree to easily find the process, because the searching time in a tree is logarithmic. And an element of this, in abstract words, array, is a process descriptor, or PCB, a process control block. It contains all informations that differ this process from other processes. For example, state, ID, owner, parent process, head of list of children, and so on. So you can see here the elements of a record describing a process on various levels of abstraction. This is in microkernel. This is in the highest level of process cooperation, in memory management layer, in file management layer. Okay. So the operating system allocates memory, splits virtually a processor to a set of virtual processors, and separates the processes. Every process runs its own program, and they are separate, that do not touch each other. It is the state of beginning of concurrency in computers. Quickly, the programmers started to build programs that cooperate. So they need not be completely separate. And initially, there were no mechanisms to arrange process communication. Users strongly ordered such mechanisms from operating system manufacturers. And they created some mechanisms. For example, in Linux, you have pipes. Pipes are just memory areas to which processes can write and read in FIFO manner. Other systems offer more flexible, just arrays in which we can insert in given cell with specifying of the index of the cell. But every access of this common resource must be done through the operating system. Writing to a file in Unix is writing to a file, to a device, and to a pipe are syntactically identical. They are system calls. Formally, we assign to a given stream a file, a device, or pipe. This sequence we already know. This is the sequence of handling an interrupt. There are some additional elements that we did not discuss. For example, when we have wire OR on interrupts, it is operation when we can join the wires of interrupts together without any logic gate, because the wire itself realizes the logical OR function. It is called wire OR. In such a situation, when the interrupt comes, operating system does not know which device caused the interrupt, because many devices are connected to the single wire. So it polls all devices connected to given interrupt line, asking which one sent the interrupt. Nowadays, in many systems, it is automatized. For example, in PCI Express that we have in our PCs, the bus controller polls all devices and informs operating system after polling which device caused the interrupt. But generally, it is what we already know. The interrupt handling differs mainly in this part because it's different for device interrupts. It is waking up a process. Different when it is system call, for example, providing current time to the process. So this part differs, various interrupts. This part and this part is exactly the same. Of course, in extra code, we have no polling devices, but generally it's the same. It seems to be simple. However, in very simple kernel, those instructions can take 100 or 200 instructions. In complicated operating system like Windows and Linux, it can take more than 1,000 instructions to switch from one process to another. Those operations are costly. So we have a barrier between the process and the kernel, and crossing this barrier is very expensive. When we have two processes that cooperate, having common resource like memory field, both of them should cross this barrier. It is double costly, we can say. When we have a pipe in Linux, sending to a pipe process must cross this barrier, and receiving from a pipe must cross this barrier. It's very expensive. So the users said, I want my processes to be protected from processes of other programs or users. However, those two are both my processes. I don't want a barrier between them. I want them cooperate easily and fast. I need not, I want them to be protected from others, but I need not any protection between them, because this is my process and this is my process as well. I am responsible if something went wrong. Blame me, I am responsible. However, not in cooperation with other programs in which the barrier should be strong as before. That was the reason why the engineers invented process groups with some simplified barrier between processes. And then they invented threads. Threads can use common memory area, common resources located in this memory area, without asking operating system for permission, because those addresses are available to the process as any other address inside the program. Such a way, we have a construct in which user threads have strong protection against other programs. It is normal inter-process barrier. But inside the process, we have threads with the protection lowered to smallest possible level. They need not call operating system to cooperate. That there is the reason of inventing the threads. Between threads, we have weaker security, but the owner is the same, is the owner of the process. They share all the resources. It means that if one of threads allocates some resource, it is available to all the threads in the program. For example, a thread opens a file and all threads can read and write this file. Resources available without system calls. Of course, not all resources. If it's a file, we must perform a syscall. But if it's memory area, we can write and read freely. Problem with synchronization. If a system has full knowledge about the threads, it can arrange synchronization between them. But in simplified solutions, when a user program is responsible for creating and running the threads. A user must synchronize them. In such solutions, there are no operations like wait for an event by the thread, like there are for a process. A process can wait for an event. A thread cannot wait for an event. Instead, we have withdrawing from using from the processor. A thread leaves the processor and asks some part of the program to choose another thread to run. This difference is between, we can say, user-level threads and system-level threads, and we return to this issue later. What a task needs, not a task is a common name for threads and processes. What a thread must have to run. Assuming that starting a program, we organize the memory for the program, like the code, data, and in data it is a stack. A thread needs only a stack, because all other data are shared with other threads. So, of course, stack and registers of the process. So, if we switch between threads, we must save the register of one thread and restore of the second thread. So, some cost of switching between threads still exists, but the cost is extremely reduced compared to processes. And in multiple CPU, the threads can run really in parallel, because they can run on different processors, if they are system-level threads. If there are user-level threads, then they must interleave on a single processor. So, if we have the old-fashioned operating system based on processes, we have processes that are separated from another, one from another. If we have modern operating system with processes and threads, we understand processes as former static view of the process. It's set of resources allocated to a program to run. And the dynamic aspect of running a process was shifted to threads. Threads took the dynamic aspect of a process, and a process preserved the static view, which is set of resources, distinguished from all the resources to run a program. So here we have a comparison. In process management, the process has the address space, global variables, open files are per process, child processes. When a thread creates child process, another thread can kill it, because they belong to the same process. Alarms, signals, and management of signals, and some accounting data, for example, some limit of time of execution. On the thread management, we have registers, including program counter. Every thread has its own program counter, so they run in parallel in the code. An own stack and own state. One thread can be suspended while other is running. This picture is from Tannenbaum. And I don't like this picture very much, but maybe if I have time, I will prepare the better one. Those worms are some imagination of threads that are running. That's why they are curves. Every thread has a stack. This is a stack. Why it is split into pieces? Because on the stack we have stack frames for individual functions. This circle is a process. So we can ask, oh, this is the kernel, not the microkernel. This is operating system in the Unix nomenclature. So we can ask, what is this area? Nobody knows. Other processes we can are here. I don't know. And this is the difference between system level threads and user level threads. Here we have two processes, and here we have two processes. Here we have 3 threads in the process and 4 in this one, and the same here. However, we see something distinguished from the program that is called runtime system. Runtime system in operating system is well-defined entity. So for me, it's not good name. It's better to say it is thread library. We can use some library of functions for creating threads, closing threads, and interleaving threads, just waving from the processor to and giving the processor to another thread in the same program. You see that here is the thread table. So we can, for example, wave from processor and appoint given thread to run. And there is for sure some function in library to switch to between current thread and appointed thread. Or we can wave from processor and say run any task, any thread. Or for sure, there is such a function in this library. So it is library of functions that operates on stacks and allow to switch between threads. But remember, all the threads run as on a single processor. The parallelism between the threads in this solution is interleaving between threads, even if we have many processors in the system. The kernel, the operating system, does not know anything about those threads. The entity that the system knows is a process, and it allocates processors to processes, not to the threads. The process is split to threads internally without knowledge of operating system. Here are system-level threads. In this solution, we have threads running in a process, but the thread table is moved to the system. It is common for all threads in the operating system. It's a single thread table. So operating system can switch between threads, synchronize the threads. Of course, every reference to the thread to do something with the thread requires system call. Here it requires just running a library procedure. Here it needs a system call. But all the resources are common virtual threads. The threads can run really in parallel. For example, if we have two processes, two threads in a single process can run in parallel, physically in parallel. And why? Because the states of threads are in this table, and scheduler has access to this table and can choose two threads from a single task, from a single process to run. This is combined solution in which we have system level threads, and every system level thread can be split into user level threads on user level. This hybrid solution is used in Solaris. You can see an example. A set of processors, set of system level threads, allocation of system level threads to programs, and user level threads in various configurations. Here we have two system level threads, and every system level thread has one user level thread. But here, common system level thread has two user level threads. Solaris is a real-time system, so such solutions are needed for effective control over devices. Okay. Oh, I have one message to you. On Thursday, 7 p.m., there will be a tutorial on Phoenix system. It will be provided by Mr. Grabski, and it will be transmitted via Teams and recorded. Now let's go deeper in scheduling. Scheduler is a part of the kernel. It chooses next process to run. However, this view, which is repeated by the authors of the books on operating system, is too simplified, because it is one of schedulers in operating system. For example, in Zilberschatz or in Stalling's books, you have some scheduling algorithms that are enumerated one after another without the distinction on which abstraction level they are used. For example, when we have SJF algorithm, so shortest job first, it's an algorithm to give access of the jobs in the batch to the computing system. On the other hand, we have round-robin algorithm. Round-robin is allocating, it is time slicing, allocating short periods of a processor to consecutive processes. It is on the lowest level on processor allocation. So the first algorithm, SJF, is not in the microkernel of the computer. it is on process management, program management level, very high in the hierarchy. Processor allocation is very low in the kernel. It's the lowest level of scheduling. But those algorithms are enumerated without their relation to the levels of abstraction, just one after another. So I will try to explain to you which manners of scheduling are responsible for which levels of abstraction in operating system. It's important, and you cannot find it in the books. But first, before we will talk about the specific scheduling algorithms, let us discuss the properties of scheduling methods. The scheduling can be preemptive or non-preemptive. Preemptive means, there are separate slides, so I will explain in detail later. The second distinction, second classification, is about importance of processes. Maybe all processes are treated equally without any distinction between them, or some processes are more important and some are less important. For example, in real-time system, most important are processes with hard time limits of execution. Then middle are processes with soft time limits. And on the bottom are the processes that are not related to time anyhow, like a process for addition of user program. If it's real-time system, user sometimes must wait for reaction on its action because real-time processes take time for controlling devices. And time allocation, limiting the time of allocating resource or not limiting. Another example that this should refer to given level of abstraction. If we allocate a printer to the process, first, we will not use round robin, not a single line for one program, second line for second program, third line for third program, and again for first program. It's stupid. So on this level, we cannot use round robin. And we cannot use time limiting. So we will interrupt after 3 pages. We let other program print, and then we return to our program. It's stupid. So in scheduling, we must always relate given property and algorithm to level of abstraction and to the characteristics of what? Of the resource. Every scheduling is scheduling of access to resources. If we have more resources of given kind, that there are processes we need not to schedule. If we have 5 processes and 1,000 of printers, we can give 10 printers to every process, let them print. Scheduling always takes place if we have potentially or actually less resources than processes that want to use those resources. So limiting the time is for short-term scheduling, bottom-level scheduling, scheduling with access to processor. And different requirements for different environments. We will discuss what what requirements are for what modes of operation and environment. First, let us describe what is non-preemptive scheduling. Preemption generally is taking back the resource from the user program, in abstract meaning. But it is realized as a decision who's next to use the resource and the moment in which the decision is made. Let's look. A process which is less important or equally important, but not more important, runs, and some interrupt. As a result of this interrupt, more important process appears. It is started or resumed, whatever. But you see that we resume this process or start, however, it does not get the resource. The resource is still allocated to process 2. If less important process waits from using the resource, we can allocate this resource to other process. This is non-preemptive method. We do not make the decision at once when the conditions change. We wait to some other occasion to change the process. Let's look at similar scheme. Less important process runs, some interrupt occurs, a more important process appears, and we suddenly allocate the resource to this process at once. It is preemptive. So preemptive means if we wait until the process waits from the resource, or we take back the resource from the process at once and give to other process. This is preemption. Okay. This is preemption. So preempting is when the decision is made immediately, and non-preemptive, we wait for some opportunity to make the decision. Priority and non-priority. Non-priority scheduling means that we treat all the processes equally. No process is distinguished somehow. Prioritized is giving the processes some numbers, and those numbers are priorities. And allocating a resource to a process, operating system looks at this number and compares those numbers. Who has higher number or lower? It depends on the system. In some system, higher number is greater priority. In some system, lower number is higher priority. It looks at priority and allocates according to priorities. Priority can be static. That means that we give some priority when process starts, and process continues with the same priority. Of course, we can change the priority, but it requires some intervention to change the priority. Dynamic component of priority is some number that changes according to the circumstances that currently are in the environment of the process. Typically, it is enlarging the priority when the process waits for resource. The longer process waits, the higher is priority. It's typical. However, it can be some other scheme. These are not rules, but algorithms, some typical algorithms used in operating systems for non-priority and priority scheduling. Non-priority is the algorithm of round robin is typical non-priority scheduling. We give the resource to the process. On the next occasion, we move the circle on some angle, that another clockwise. So next will be this one, this one, this one, this one, and again this one. So someone imagined this as round robin. Priority, we have a stack or a queue better. A stack is in Zilberschat's book, but it's a prioritized queue. What is on the top gets the resource. If it stops for some reason, we take the next one and give it a resource. And combined method, a queue of round robins. We give the resource without any distinction to processes on the top. When all of them come to inactive state, we move resource to lower, and again we act in a round robin manner. And the last property is limiting the time. In the literature, limiting the time is not a preemption, generally. Excuse me. Some authors assume that limiting the time is preemption, but generally we distinguish those two. Preemption is taking back the resource from the process, not because of time limit, because of some other reasons. If it is time limit, it's not preemption, it's limiting the time, because typically when we limit the time, we can allocate this time again in the future, like this. Process 1, process 2, process 1, process 2. We guess that it comes from round robin algorithm. When the taking back of the resource is because of waiving from using the resource, it is non-limiting the time. When timer interrupt causes taking back the resource, it is limiting. It is not preemption. Okay. Sometimes it is not every interrupt, but every end interrupt. So time limit says that at most after T, some decision must be made. It can be decision to give the resource to the same process as before, but it is a decision. It is not just that the process is taken and operates. We make a new decision to not to withdraw the resource from the process. Features of good scheduling. Justice. Every process will eventually get the resource. Of course, this requires the system to be schedulable. If we have one and slow processor and thousands of fast tasks to be calculated, maybe that some of the tasks will never get a processor. But because the system is not schedulable. The system must have some spare computing power to be schedulable. There are some rules for that. We will not deal with it. When you come to some real-time systems tutorial, you can learn what are the conditions and in numbers what should be the spare computing power for the system to be schedulable. We need not come to details, but justice say if the system is schedulable, justice means that every process eventually will get the resource. No process will be postponed forever. It does not time that every process gets the same conditions. Maybe some process will get the resource in a second and the other in a minute. But minute is a finite time, so it's okay. If it's guaranteed, that's no more than minute. And compliance with policy. Scheduler is the realization of general scheduling policy of the operating system. For example, we treat some processes better, some worse. For example, if we have some process that calls many input-output operations, like backup process. It reads from one disk and writes to second disk, and again reads from one, writes to second, and it repeats it thousands of times. So, what we can say of such process? This process almost always waits for a disk readiness. So first look is, oh, backup process is not important process. Let us give this process low priority, low computing power. But when we analyze, this process does not occupy our computing power because it mainly waits for interrupts. We, of course, know as high as real-time processes, but we can enlarge its not a priority because we will maybe priority, maybe other means in which this process will become more important than, for example, calculating process that calculates some integrals, for example. So we impose some macroscopic properties to the system, and scheduler should treat the processes to match the general assumptions of the computing system. Oh, efficiency, of course, it is important. If we can choose less and more important, we always choose less or more efficient. We always choose more efficient allocation strategy. For batch systems, we measure batch systems in nature are offline. The user gives the program and data and gets the results after hours. So for the scheduling, the basic parameter is throughput. How many jobs we can run in a quite long time unit, macroscopic, like an hour or a day. And time in system, time from getting the job by the operators of the computer to providing the results to the user. It is time in system. We can act to minimize this time in batch system. And recall, the main reason of establishing batch processing was utilization of processor. Because formerly the processors, before invention of interrupt, the processors spent time in testing the devices. So after invention of interrupt, the processors are utilized much better, but maybe not fully utilized. So the utilization of processor is very important parameter in batch system. For interactive systems, of course, it's response time. Because interactive system is a system in which the computer answers the prompts of users. So we should minimize it. So we can treat some background processes badly, but to shorten the time of reaction to user actions. And proportionality. It shouldn't be so that one user has quick responses and the other users waits for minutes. It's proportional. If we add new user to a system, all old users should face the same slowdown of operation. Proportional. And for real-time system, the scheduling, the macroscopic features of scheduling are obvious. It is just keeping the limitations of time, hard requirements or soft requirements. And predictability generally is schedulability. That the system is schedulable. That means that all processes can run. No process is deferred in time forever. These are typical scheduling in batch systems. So it is on highest level when we give access to the job to the computer as a whole. They are first come, first served, the counterpart of FIFO, first in, first out. It of course, this algorithm supports justice. However, when we are to shorten the time in system, first come, first served is not the best algorithm. SJF is much better. SJF is shorted job first. The question arises, how we know the time the job will work? Of course, in such systems, it is declaration of a user. a user declares, my program will run for an hour. Of course, it should be supported by some penalties if the user does not say the truth. A user claims that an hour, but we see the program runs for 6 hours and not finished. So in such systems, a user gets some penalties if the declaration is not the truth. Let's look at the example. We have 4 jobs to calculate on a single processor. A, B, C, D. When we run them in this order, A, then B, then C, then D, A finished after 8 time units, B after 12, because it's 8 plus 4, and 16 and 20. Of course, assuming that the job is running all the time, because jobs, if they use the devices, they interleave. While one job waits for readiness of the printer, the second can operate. It is just ideal circumstances just to show what the rule means. If we first run short jobs and long jobs, and the end, we have 4, 8, 12, and 20. So the final is 20 here and here, but here we have average of 13 time units or 14 time units, and here 11 time units. So in average, a user waits shorter for the result of his job. Of course, it is on assumption that the jobs do not interleave. If we have many processors, of course, we allocate here, for example, here, B to the first processor, C to the second, assuming that we have 2 processors, they run. If B finished, we take D. If C finished, we take A. We always take the new shortest job if the previous job finished on this processor. Sometimes many events influence the run of a program. So it can happen that a program was taken to run, but it was suspended for some time. So there is a variant of this SJF rule is SRTN, shortest remaining time. Because the circumstances can change over time, so we do not take the absolute time. We just let the shortest remaining time to finish first, and then we take the next one. So it takes into account some dynamic conditions which change the relations between processes that run. I told you that it is important on which level of abstraction we understand this scheduling. Again, this is the picture from Tannenbaum. This time is very good because it describes what kinds of scheduling are on different levels of abstraction. Here it is admission scheduler. So it is used in batch systems when we allow a job to enter the batch. It is to schedule the computer as a whole. The resource is the computer as a whole. Maybe because the computer is overloaded, we let only part of the queue of waiting jobs to run on a computer, and some are suspended temporarily from entering the computer. The second level, the middle level, is letting the programs to take some memory. Because if we allocate some resources needed to run, the previous to last resource to allocate is memory. We split memory between the jobs. If the memory is full, we cannot allow next they are admitted to the system. We know about them. We allocated them some maybe virtual resources, but physically we wait if there is enough memory, and we allocate memory. Is the second step, we can say. We allocate a computer as a whole to a job, then we allocate memory. Finally, we allocate a processor. It's the last resource allocated to the process. So it is high-level scheduling, middle level, medium level scheduling, and low level scheduling. Here we can use shorted job first. Here we can use round robin. Here we cannot use round robin, and here we cannot use shorted job first. So we must understand to which level of abstraction given algorithms are deserved. If we build the states of processes in systematic way, hierarchical way, not the way that we saw in Unix, we can build it as hierarchical system of resources. We know current and ready are two states related to the processor. So this is a state in which a process has a processor. Here, a process waits for a processor. The resource for which we wait is given in a balloon. We can name both of these states active. Active is having a processor or not, but can run at any time. The opposite of which is blocked, in which a process waits for some event or condition. So it waits for some condition. Now it is the same scheme as we learned before, but those two states are surrounded by a common abstract state active. And I explained to you that blocked typically is judged, blocking and unblocking is judged on higher level of abstraction. It's not in the kernel. We can treat those two as a common state residing in memory. On the other hand, it is swapped out to the disk, because we can sweep it out again. Tannenbaum made an error, and I made this error as well. Sweeping and swapping are different mechanisms, and I will return to this later. It is swept out. So it is on the disk. When we temporarily, this task cannot continue, but when we load it to memory and we sweep out another process to the disk, it can continue. So it waits for physical memory. Again, we can surround this with name operative, and the opposite state is inoperative. We do not mention here physical memory, but we mention virtual memory. The process is not even taken into account to operate in virtual memory. It's inoperative. And again, admitted, like in previous example of three-level scheduling, and not admitted, like in job systems, admitted and not admitted. And the computer itself is the resource to which we admit the job. It's built more hierarchical and splits the responsibility to some levels of abstraction, higher and higher. Okay. Do we have time to discuss it? Oh, we can start. As an example of very good scheduling system, I want to present you, it is scheduling in access to processor, only processor, not memory, not the devices. It is real-time system. This system was used in real-time solutions, and it was used in excuse me, in CD drives and DVD drives. So most people over the world used this system, but almost nobody knew about the fact. Because it is CD drive is embedded system, and we do not look inside to watch what operating system is inside. Nowadays, it is not so popular, but it is used in real-time system under different name. And let's discuss the rules that was used in this real-time system. The entire scheduling is based on two values, two system variables, max age and min priority. They are system variables available to the administrator. He can change their values, but typically they are not touched. They just define some range of values between min and max, and every process individually has its base priority. It's the property of a process, not of the system. It's given process. When the process does not get a processor, the priority rises from base priority, and it rises until the process gets the processor. And here the priority is suppressed down back to the base priority. And again, the priority starts to rise. It does not rise forever, because if it reaches max age, it stops rising. Here, it's shown here. It gets the processor, so the priority is suppressed again to the base priority, and so on and so on and so on. This rule of scheduling is called aging. It is called aging because the elder is the process and does not get processor, the priority is higher. And which process gets the processor? Highest priority process gets the processor. Here the process got the processor, so we judge that other processes had lower or equal priorities. So the process got a processor, and its priority was suppressed back to base priority. Let's look what happens if you have several processes. These are current priorities of 4 processes. This process gets the processor, it's solid line. After that, process 1 is, its priority is suppressed to base priority, and all others are increased by 1. Process number 2 gets the processor, it is suppressed to basic, and all others are increased by 1. Number 3 gets the processor and is suppressed, all others are increased by 1, and so on and so on. If we observe a set of processes, now it's simplified because all processes have equal base priority. Next week, I will show you what happens if they have different base priorities. Thank you for today.